Boltzmann theory. So we'll start talking about the electrostatic interaction. We will talk about Boltzmann theory, and then we will go for Debye approximation, and from there we will go to electrokinetic forces. So that will cover up this portion of the module, and then we will next from in the next class we will be moving towards contact angle and all those things. Okay, so I will make it short for contact angle, that portion, but this portion will be a bit elaborated. Please bear with me, and we will do couple of derivations which will be important for your semester. But this portion will be excluded from your class tests. Okay. So class test will be, as Tomojit informed me, it will be on this Saturday from 7 or what time?
Yes, ma'am, from 7 to 8:30.
7 to 8:30. Okay. Okay, so without wasting further time, let us directly go to today's discussion. So we have talked about what is electrostatic interaction a bit in a nutshell in the last class, but we will actually go into a bit more detail about electrostatic interaction and what is a double layer formation, and in this particular class. So as I mentioned in the last class, if we put a charged particle in a suspension with ions, then the primary charge will attract the opposite charge ions by electrostatic attraction, and obviously the counter ions will come closer to the counter ions will come closer to the surface of the particle, as well as the co-ions will be little bit farther from the surface of the particle. Okay, so in that way what will happen, you will see a kind of a electric potential, which if I put it in the psi naught on the surface of the particle, then it will decay with distance from the particle. Okay, and you will see a ionic concentration that is basically differ from for counter ions, which is basically decreasing in nature, whereas co-ions will increase with you know with increase in distance from the surface of the particle. So that is basically in the nutshell what we have talked about in the last class, and we said that when there is a positive or negative charge on the surface, then obviously the counter ions will come closer to the surface, and it seems like there is a kind of another layer of particle or another layer of charge will be in the liquid or the fluid side. Okay, so then there will be a charge on the particle surface, and there will be a counter ion charge on the just on the side of the fluid. So in that way you can say that there is two layers of opposite charges will be present if you just put a charged particle in an fluid, or in a either in gaseous phase or in the liquid phase. Okay, and if it is in dispersion, then you find this kind of phenomena, and that means there are two layers that has been formed, and that is why it is known as double layer. But we have also seen in the last class in a bit again in a bit in very crudely, that if these ions, counter ions, are very close to the charged surface, and they get all the counter ions comes in closer to the charged surface, then obviously there will be a fall of interaction energy or the potential, and you will see the potential like this rather than exponential decay of the potential. But this is not exactly the right case or real cases, but this is an ideal case, and that is basically known as or assumptions for Boltzmann theory. So we will go to that. So we can say that since a solution is electrically neutral, so we can write summation of I Zi Ni naught will be equals to 0, where Ni naught is the bulk concentration of the ion or the number of ion per unit volume, and Zi is the valency of these ions. Okay, you can either put the valency in absolute form, and then you can calculate it, and we will see that. We will see how we can actually go for the absolute value and not for any charges. Okay, as a sign convention for valence, we usually use negative sign for counter ion valence and positive sign for
ঘুমালোর ঘরে টিচার ছিল যেটা স্যার পড়াবে আগে আগে পড়ে চলে আসতো দিয়ে পাতাবে পাঠ তো যেগুলো এমন ভালো র্যাঙ্ক করে
মাইকটা বন্ধ কর।
আরে সুমন মাইকটা অফ কর।
That's fine.
Sorry, ma'am.
Okay, so basically depending on whether you are dealing with the co-ions or counter ions, depending on that we do have different signs for valency, and by convention Z is negative for counter ion and Z is positive for co-ion. Okay, and so if
ঠিক আছে তুই চলে আয় আর
if we put the potential energy of an ion of a solution as phi, then we can actually relate that with the surface potential, and that will be equals to Ze
হ্যাঁ ম্যাম স্টার্ট করে দিয়েছে
Ze into psi. Phi will be equals to Ze into psi. So where psi already I have mentioned this. This is the electric potential at a ion location, and E is the charge on an electron, and variation of the potential with distance from the charged surface is basically given by the Poisson equation, which can be written like this: del square psi equals to minus rho by epsilon, where rho is nothing but the charge density of the system, and epsilon is the absolute permeability of the electrolyte. So epsilon, we can write it in terms of epsilon naught into epsilon r, where epsilon r is the dielectric constant of the electrolyte, and epsilon naught is the dielectric constant in vacuum. Okay, so the charge density at any location can be written by this equation over here. Rho will be equals to summation of I Zi into E into Nix, where Ni, already we have mentioned that Ni is the number of ions per unit volume, which is basically a function of X. Okay, so we see that the charge density as a function of X, and in order to solve this Poisson equation over here, we have to calculate the charge density in terms of electrical potential. For this, we have to calculate the Ni first, and then only we can do this calculation of charge density, because charge density actually incorporated a term of Nix, which is we need to first find out, and then we can go for the other part of the calculations. So flux at any point in the electrolyte can be defined by the number of ions crossing per unit area per unit time at that point, and this flux will be dependent on the concentration gradient of the ions of the electrolyte and the electric force of the ions due to electric field to the plate. So the flux J can be written in terms of minus D. D is the diffusivity, okay, or diffusion coefficient, into dn dx plus n into v, where v is the velocity of the ions, and d is the diffusion coefficient or diffusivity of the electrolyte. So the first term of this expression, that is basically this term minus d into dn dx, is due to the concentration gradient, which is called the conductive flux, and the last term is basically the convective flux. Okay, and we can write force by friction factor is equals to V, which is
So, ma'am, N into V is what? Term is what? What flux?
N into V is, I mean, this is for the convective flux. This is for conduction and this is for convection. Okay.
Ma'am, could you please put the slide on full screen mode?
Before slides.
Ma'am, full screen, ma'am.
ফুল স্ক্রিনে?
হ্যাঁ ম্যাম।
ফুল স্ক্রিনে না আমার লেখাগুলো দেখতে পাবে না, আর স্লাইডটাও বোধহয় চেঞ্জ হবে না।
আচ্ছা আচ্ছা ঠিক আছে ম্যাম।
দেখো তো স্লাইড চেঞ্জ হচ্ছে? স্লাইড চেঞ্জ হয়েছে কি? আমি স্লাইড চেঞ্জ করেছি।
ম্যাম প্রবাবলি ফুল স্ক্রিন এখনো হয়নি।
ফুল স্ক্রিনটা হয়নি,
ফুল স্ক্রিনটা হয়নি।
আমার এখানে ফুল স্ক্রিন দেখাচ্ছিল অ্যাকচুয়ালি। দেখো তো আরেকবার, এ দেখো, দেখতে পাচ্ছ আমার ফুল স্ক্রিনে?
না ম্যাম।
না ম্যাম।
ম্যাম আপনি প্লিজ কন্টিনিউ করুন তাহলে।
আচ্ছা আমি কন্টিনিউ করছি, কারণ ওই ফুল স্ক্রিনে একটু প্রবলেমই হয় অ্যাকচুয়ালি। এটা যেহেতু একটু 2010 গুগল মিটের সাথে একটু প্রবলেম হয়ে যায় সেই জন্য। ওকে, সো উই ক্যান রাইট that force by friction factor, we can write it in terms of V. Okay, so force of an ion we can write in terms of this d phi by dx, and this V we can write it in terms of force by F. So it will be given equals to 1 by F into psi Ze by dx, because d phi already we have mentioned in the last slide over here as Ze psi. Okay, so that's what we have actually put it over here, and we get expression for V over here. Now you substitute V from this equation to this equation over here and simplify it, you will obtain this kind of equation where flux J equals to minus d dn dx plus n into d phi divided by F into dx. Now at steady state there will be no net flux, that is nothing but convective term will be equals to the conductive term, and that's why we can write J equals to a whole this thing, it will be equals to 0. Now এক মিনিট, কেউ একটা এন্টার করতে চাইছি। আমি আজকে একটু তাড়াতাড়ি পড়াচ্ছি কারণ অনেকটা জিনিস কভার করব সেই জন্য, বাট এই পুরো নোটসটাতে সমস্ত কিছু এক্সপ্লেন করা আছে, প্রত্যেকটা স্টেপ ডিরাইভেশনস অলমোস্ট করা আছে, আর যেগুলো সিম্পল কিছু কিছু এ রয়েছে সেগুলো তোমরা নিজেরা পড়ে নেবে, ঠিক আছে? ছোট ছোট একটা দুটো স্টেপস।
ওকে ম্যাম।
ওকে ম্যাম।
In the general expression for diffusion coefficient, we can all, I mean, mechanical people already know this. So diffusion, we can write it in terms of limit t going to infinity delta r square by t, and also we can write it in the simplified form as delta r square root of delta r square into delta r square by t. So this actually can be given in the variance form of delta r square, and also in the force field form of delta r square divided by the friction factor. So basically, if you just look at this over here, it is of the order of something like kT, and that kT which is around kT, so we can write diffusion coefficient equals to kT by F. If you could remember it, I don't know whether probably Shashwata sir has already talked about the Stokes Einstein equation, and that is something like this. If you can correlate with that, okay, where kT is the energy for thermal diffusion, kb, this is basically nothing but the Boltzmann constant, and this is the temperature, and this equation is basically known as Einstein's relation to for the Brownian motion of the particle. And obviously we can assume validity of the Stokes law to find the friction factor. So if we put this, if you just take this, if you substitute f from here to the other equation, and if we just simplify it, আমি এখানে equations গুলো নাম্বার করতে ভুলে গেছি, but if we just simplify it, if we just put f into this equation, replace f into this from this equation with d by kt, then obviously, kt by d, then you will obtain this equation over here. So this equation will become as minus d dn dx plus nd divided by kt d phi dx will be equals to 0. So just we have simplified it, and you will obtain n will be equals to c e to the power phi by kt. I hope this is visible to you. This is nothing but n equals to c into e phi by kt. So this c will be the constant of integration, which can be calculated by applying the boundary condition. So when the potential energy is 0, the number of poles per unit volume will be equal to n naught, which is equals to the concentration far from the surface. And this can be used as a boundary condition. So thus, when f equals to 0, n equals to n naught, so c will be equals to n naught. And by using that equation, you will obtain this over here, and you will obtain c will be equals to c naught, n naught, and you can put it into this equation to obtain, this is my final equation for the for Ni. Now, once we obtain this equation over here, the potential energy of an ion in terms of electrical potential can be given by phi equals to Ze psi. Already we have written this also. So, so basically we can put
একটা প্রশ্ন, there is one question that in equation that in the equation d into dn dx plus nd by kt d phi dx is equal to 0. If I eliminate d, then the next step becomes dn dx plus n by kt. Oh, d টা হবে না,
এডিটা নেই, একদম কারেক্ট। আমি জাস্ট ওটাকে অমিট করতে ভুলে গেছিলাম, কারণ আমি যেখান থেকে ইকুয়েশনটা নিয়েছিলাম ওখানে ওটা ছিল, আমি তারপর অমিট করব, আর একদম খেয়াল নেই। ওকে, এডিটা হবে না। থ্যাংক ইউ সো মাচ ফর দ্যাট। Okay, now so the potential energy already is given in terms of the electrical potential, and that you can replace over here in order to get Ni in terms of psi. Okay, and now we can put this equation into the charge density function, and you will obtain the charge density rho will be equals to summation of I Zi E Ni naught exponential minus Ze epsilon by kt. Okay, so this is basically the final equation for charge density, which if we put this charge density into the Poisson's equation, then we get this equation, which is known as Poisson-Boltzmann equation, and on solving this equation we can obtain psi as a function of x. Okay, so how the electrical potential is changing from the surface of the particle is given by Poisson-Boltzmann equation, but unfortunately the thing is you don't have a direct solution for this Poisson-Boltzmann equation. Rather, we use certain assumptions in order to go for in order to obtain certain correlation. Okay, and from this equation we can actually find out whether whether the particles or the colloids are stable in nature or not. So we can predict those things. So whether coagulation can be achieved or not, those things can be actually predict from this Poisson-Boltzmann equation, and that we will see within couple of minutes. We will try to see the Dlv theory, and from there how we can correlate that. Okay, so next we come to the, not next, but we come to the Boltzmann theory. So Boltzmann basically solved the Poisson-Boltzmann equation for symmetric electrolyte. We will see Debye-Huckel equation for asymmetric electrolyte. So by symmetric electrolyte, we mean an electrolyte in which valence of counterions and coions is same, like NaCl. Okay, so sodium chloride is an symmetric electrolyte, whereas if you are talking about the aluminum chloride, that is AlCl3, that is basically a asymmetric electrolyte. Okay, okay, now in order to solve, when he solved this equation, he multiplied the Poisson-Boltzmann equation with 2 dψ dx with that, and he obtained, actually break the order of the equation, and then you can put it in this form: ddx of d psi by dx whole square will be equals to ddx of 2 kt by epsilon into this whole term over here, which is basically Zi, which is the surface charge density term. Okay, now if you integrate this equation over here, and you apply the boundary condition, d psi dx will be equals to 0 and psi will be equals to 0 as x is going to infinity, and at x equals to 0 psi is psi naught. I don't put that, but that is another boundary condition. But if you just put this boundary condition, you will obtain this equation over here: d psi dx whole square will be equals to 2 kt divided by epsilon into the charge density function. And if you just go for the condition of symmetric electrolyte, this equation can further be simplified by like this. Okay, where n naught over here is the bulk concentration, and z is the absolute value of valence. You don't need any signs for this, whether you are that means whether you are dealing with the coions and counterions, it doesn't matter. It's only after you calculate everything, you just put the this is just the potential variation, so you don't need to have whether how the concentration is changing. So for concentration change, you have to put negative sign for counterions and positive sign for coions. So
what is basically means the represented physically by psi? Can you tell? In this.
Okay, psi is a kind of a, we will go to that part in a little later, but what it does mean is আমি জানি না তোমরা শুনেছো কিনা zeta potential. Did you heard that?
Yes, ma'am.
Yes,
ma'am.
Right.
Yes, ma'am.
So basically this is zeta potential can be measured, right? That is on the surface of the particle. Usually what is zeta potential, we will talk about it, but how that potential basically changes across from the distance from a particular particle surface, that is basically given by this equation: decay of the potential. Okay,
okay, means psi is zeta potential.
psi ta zeta potential noy. Okay, psi is the surface potential that is basically getting decayed but we will actually, we cannot measure the surface potential directly. What we can measure is, we can measure the zeta potential. Okay, so that part I am coming within a couple of minutes. Just give me a little bit time. Okay, আমি এক্ষুনি ওই ডিসকাশনটা ঢুকছি না, ঠিক আছে?
ওকে ম্যাম।
জিটা পোটেনশিয়াল আর সারফেস পোটেনশিয়ালের মধ্যে একটা বেসিক ডিফারেন্স আছে, যেটা আমি জিটা পোটেনশিয়ালে ঢোকার সঙ্গে সঙ্গে বলবো, ঠিক আছে? But measurable quantity is zeta potential. Okay, now if we take this, in order to solve this equation, if you take y equals to Ze psi by kt, then you can obtain, you can simplify that equation by like this, and we can solve that by having this equation over here, the solution, where k square, this is basically k that we are having over here, k square will be equals to 2 e square z square n naught divided by epsilon kt, and c is the constant of the integration. Okay, now if you again apply the boundary condition that x at x equals to 0, psi equals to psi naught, and substitute the value of y for this equation, then you will obtain this final equation over here. This is the final equation for potential decay. Okay, and if you just want to put it in a simplified form, then you can write it in terms of gamma psi will be equals to gamma naught psi naught exponential minus kx, and this psi we have defined, this gamma we have defined it as e to the power z e psi divided by 2 kt minus 1 divided by same thing plus 1. Okay, so and this k, okay, আমি একটু পরে আসছি k টা ডিভাইডেন্টটাকে আমি একটু পরে ডিফাইন করছি, but anyway, so this is the basically the equation for decay of the surface potential. Okay, দেখো একটা এক্সপোনেনশিয়াল ডিকে টার্ম তার মানে ইনকর্পোরেটেড হয়ে গেছে অলরেডি, রাইট?
Yes, ma'am. Yes, ma'am.
আচ্ছা, okay, so if you look at this equation over here, if you look at this equation over here, you see that there is a minus k term here, also k is there, right? This minus k inverse is basically is known as d by length, which is having a unit of length, and that is basically known as d by length. And this is how do I put it? It is basically the length scale corresponding to electrostatic interaction. That is good. And if you have larger value of k inverse, lesser the rate of potential drop with respect to x, and value of k inverse, that is the d by length, basically depends on the concentration of the ion, valence and temperature, and larger the concentration or the valence of the ions, lower is the k inverse. So that has been actually put it in this graph over here. So if you have the electrolyte concentration increases from 1 to 3, then obviously your d by length is basically decreased. Okay, at higher temperature, diffusion increases and k inverse also increases, so that the electrostatic forces become significant for larger distance. And this equation can further be simplified by putting like this: when x is large or psi is small, when psi is less than 10 millivolt, this is very, very important. When psi is less than 10 millivolt, exponential term can be expanded, and you can neglect the higher order terms. You can write Ze psi divided by 2 kt equals to 2 gamma naught exponential minus kx, and psi will be equals to 4 kt by Ze gamma naught exponential minus kx. So this is the final form of the potential, with how it will actually change in potential rather. So when x is large and psi is small. Now when psi naught is small, the above equation can be given by in this form: psi will be equals to psi naught into exponential minus kx, and this psi is directly proportional to psi naught for smaller values of surface potentials. Now this is the equation for mostly I mean, this is basically the general equation for symmetric electrolyte. But what happens with the asymmetric electrolyte is given by Debye and Huckel approximation, and they have solved the Poisson-Boltzmann equation by Poisson-Boltzmann equation using asymmetric electrolyte and for low potential. Okay. So they have written that ZIE psi divided by KT is much smaller than 1, and thus we can basically expand the exponential term in that general electrostatic equation where charge density can be written in terms of charge density will be equals to summation of ZIE Ni naught exponential minus ZIE epsilon KT, and that we can further write in this form. Okay, so these are the just the assumptions they have made, and they have gone for this kind of charge density equation, and the first term over here goes to 0 because of the electrically it is neutral in nature, so this term will be equals to 0, so this will be minus. So sorry. And so you can write rho will be equals to summation of I Zi squared Ni naught E squared psi divided by KT. Now, if you put that value into the Poisson-Boltzmann equation, you will obtain d2 psi dx square will be equals to e square psi divided by epsilon kt summation of Zi square Ni naught, which will be equals to k square into psi, where k square is nothing but e square divided by epsilon kt summation of Zi square Ni naught. And in order to solve this equation, we need two boundary conditions, and the first boundary condition is psi is equals to psi naught, that is the surface potential at x is going to 0, or x equals to 0 you can write, and psi naught is going to 0, approaching to 0 as x is approaching to infinity, and on solving this and putting the boundary condition, you will obtain psi equals to psi naught into e to the power minus kx, and we can write it in this form also. Psi will be psi naught into exponential minus x divided by k inverse, and this k inverse, or rather k to the power minus 2, is given by epsilon kt divided by e square summation of I Zi square Ni naught. So k inverse will be nothing but square root of this. Okay, and this k inverse is given is nothing but your Debye length that we have defined earlier, and only thing is k inverse decreases as Zi or Ni naught increases. Thus, if you add more salt or higher valence salt, the amount of surface potential basically decreases. Okay, and this actually becomes
সাইড লাস্ট লাইনটা একবার বলবেন?
হ্যাঁ, basically I said that if you actually in k inverse or the Debye length basically decreases with increase in Zi or Ni naught, with increase in Zi or Ni naught, and if you add more salt or more valence salt, okay, if the valency of the salt is higher, then that will affect the surface, and basically the surface potential will decrease. Okay, as well as the Debye length.
Ma'am, the surface potential will decrease. Does that mean that the surface tension also decreases or something like that?
Surface tension, yes, somehow, I mean, yes, it will decrease. Surface tension will decrease when the potential decreases. Okay.
Okay, ma'am.
Okay, so these two are important equations that you have to remember, for this is for asymmetric electrolyte, and this is for symmetric electrolyte. Or else you can go to this equation, and that should be enough for you. Okay, so this will be for this equation over here for symmetric electrolyte. Okay.
Ma'am, are the derivations important?
Yes, the first derivations are important. If I give problems, I will do some problems on this, but the problems are more or less numerical. I will not go much detail into the problem, but derivations গুলো একটুখানি করে নাও, ঠিক আছে? Otherwise 100 নম্বরের কোয়েশ্চেন করতে পারবো।
Yes, sir.
ম্যাম আমাদের তো মোস্টলি 70 তে হবে।
ম্যাম 70 তে হবে বলেছে।
ও তোমাদেরটা 70 তে হবে, হ্যাঁ রাইট, 100 না। We got it, yeah, 70. But still these derivations are a bit important. Like I haven't put all the steps for Debye-Huckel approximation, because these approximations are, some approximations which are done by normal, the numerical ones. So that one I have deliberately I didn't incorporate it. So Debye-Huckel জন্য যে ডেরিভেশনটা আছে সেটা তোমরা না করলেও চলবে, বাট বোচাপম্যানের ডেরিভেশন এন্ড ইলেকট্রোস্ট্যাটিক ফোর্সেস ডেরিভেশনটা করে রাখবে, ঠিক আছে?
ওকে ম্যাম, এগুলোকে কোনো are there any assumptions in deriving these equations?
There are several, ঠিক আছে, but only thing is it is more rigorous because it is actually considered the asymmetric electrolyte. Okay, Boltzmann theory is a more simplified version, and Debye-Huckel is a more rigorous model. Okay, now we are moving towards the Dlv theory, because we are actually now where we are interested in is we want to know whether a colloid is stable at all or not. Okay, so colloid means when you put charged particles which are very, very small, which is of the order of in the nano range actually, that is say from 1 to 100 or 1 to 1000 nanometer range. In that range, if you put particles with surface charge in a dispersion, then that forms a colloid. Okay, now these particles either will come together to coagulate, or it will stay as it is in the dispersion for a long time if there is stability in the colloid. So we would like to know whether the colloid is a stable colloid or whether that is not a stable colloid, whether the coagulation could be possible. Now, for coagulation, what we can do is we can put several electrolyte into it, like NaCl, AlCl3, like alum. Alum, all of us know that if we put alum in water, so there will be certain amount of coagulation with if there are impurities in water, right? So that's how in ancient time they purified water. So basically that is the application of all these things that we have talked about till now, and that theory, the theory that combines or that basically tells us whether the colloid is stable or not, is given by Dlv theory. Because obviously we understand that when you have two charged particles together, there will be attractive forces and there will be repulsive forces, right? And so we will sum this two up and see whether it can actually overcome the barrier of the energy barrier, and then only it can coagulate. Otherwise it will be stable as possible. So that's why we want to go for this kind of theories over here. So I'm not going to read this slide at all because whatever I said, it has been put almost in a similar way. So basically what is important, this Dlv theory has applications in predicting the stability of the colloids in a number of industrial processes such as liquid-liquid extraction, alkaline flooding operation, flotation of hydrocarbons, stability of oil droplets in emulsions, etc. Now, if you consider two parallel plates which is having surface charges, which are basically, and they have put in an electrolyte medium, okay, and they are separated by a distance d. Okay, now these plates may have an excess surface charge which can be of the reason of any one of what we have already explained, like ionization of the surface groups, dissolution of the ionic solids, ion adsorption, isomorphic substitution, any one of them, or adsorption of the ions or the surfactants, that can actually give rise to the surface charge. Okay, now if we put that, and then if we consider the surfaces have an excess charge and the total energy and the surface energy of G total per unit area, then the total energy of interaction per unit area will be given by van der Waals forces GLW plus GL, that is GEL, that is the electrostatic interaction, and plus G acid base interaction, plus there could be several other things. Okay, now if we I mean, by using the Deriaguin's approximation, we can say that the G total could be, we can write it in terms of GLW plus GEL, where the acid-base interaction can be neglected. Okay. Now, if we consider the Go-Chapman model for a symmetric electrolyte, then the GEL total will become this with this equation. GEL will be equals to 64 N naught KT gamma naught square exponential minus KD divided by K, where gamma naught is nothing but tan H of Z is epsilon naught divided by 4 KT, and 1 by K will be, that is K inverse, will be nothing but square root of epsilon KT divided by 2 E square Z square N naught. That will be going to give you the Debye length. Now, if the two surfaces have unequal potential, say 1 and 2, then, sorry, this is, the expression for GEL will become, rather than gamma naught square over here, we will have gamma 1 and gamma 2. Now we can actually put, if you see that, we are actually, rather than writing in terms of the surface potential, we are writing in terms of the surface energy. Now, it is important that you note, with increase in Debye length, GEL decreases as basically the solute concentration increases, that is N naught increases, and the decrease in repulsion favors the coagulation of the colloidal particles. So that is basically, if GEL decreases, then there will be coagulation. If GEL is not less than the barrier, the energy barrier, then you do not have the coagulation. You might have flocculation, but you might not have coagulation altogether. Now, the van der Waals forces of attraction term, we know that for two flat plates, we know that we can write it in terms of minus A 1 to 1 divided by 2L pi d square. This is the Hamaka constant, and D is the separation distance. Then G total, we can write it like this over here, and if there are two different dissimilar materials, so we can write gamma 1, gamma 2.
Ma'am, এটা total energy per unit area.
Total energy per unit area. Okay. G total ta hoche total energy per unit area. Okay. Now, that means G total is summation of a positive and a negative term, right? So there will be a attraction and force and the repulsion force both acting at the same point or at same time, right? So if you just look at the energy graph, you will understand better. So I will just try to go there. Sorry. I will try to go there and try to explain things. So this is the first one where you are having only the attractive forces. Then this is the primary minimum, and this is where you have the coagulation to take place. Okay. Now this is the energy barrier that you have to overcome in order to actually go for coagulation. There will be a secondary minima where you can find the flocculation to take place, but this has to overcome in order to have the coagulation. Okay. Now, what is the basic difference between flocculation and coagulation? Flocculation is nothing but when you have different particles coming together or flock together. They didn't lose their individual identity, and the surface area will be, there might be very small loss of surface area, but mostly the surface area will be equal to the total surface area of each of these particles, summation of the surface area of these particles. Now coagulation is something where these small particles will come together, they lose their own identity to make a bigger particle. Okay, so the surface area decreases a lot in this particular case, and obviously the individual particles will lose their individual identity in order to form the bigger particles. So this is known as coagulation. ठीक है sir?
Okay.
Okay. Now, so this energy barrier is of the order of 15 kV. Although I have written over here 10 kVt, but this is usually 15 kVt around. Okay, 10 to 15 kVt. So if your surface energy is, if your potential is having, or the interaction energy is having a more than of 15 kVt value, then you might expect that there will be a coagulation. Otherwise, there won't be any coagulation. There could be flocculation, but no coagulation. Even though if you are trying to make the surfaces coming closer to one another. Okay, now the effect of concentration. So basically, if you increase the salt concentration, this is the concentration of the electrolyte, if you increase it, then you will see this kind of variation where you will find that it moves from 1 to 2 to 3 to 4 to 5. Okay, so basically 1 is nothing but the curve for pure water, which is having very low electrolyte concentration, and the repulsion term dominates, and the overall interaction energy become positive in this particular case. Whereas, positive means it is repulsion, negative means it is attraction. Okay, so that you have to remember. Now what happens in when you have the secondary minimum starts appearing, but the energy barrier is still very high, then this is the second case, that is we are actually using over here. And in this particular case, the colloid is kinetically stable, and there might be little bit flocculation that might take place. Okay, in 3 basically the energy barrier is lowered significantly further, and coagulation may increase if it can actually overcome this energy barrier over here. So that will be of the order of 15 kVt, and although this is sufficiently low, so there might be possibility that most of the particles will overcome this energy barrier. Now in the fourth one, the energy barrier becomes 0, and you will see the first coagulation to take place, and the concentration at this point is basically known as critical coagulation concentration, at which the coagulation can start occurring spontaneously. Okay, and when with further increase in concentration of the ions, there is a large coagulation to takes place, that is in over here. So everything, and here basically attractive forces predominates, and basically you will see that there will be very fast or spontaneous coagulation that is taking place as soon as you put the particles into some electrolyte. Okay. Next, we are going to move now towards, after we have this kind of discussion, we move towards what is the surface charge, and from there we will talk about zeta potential. Okay. So just look at this figure over here. So if this is the surface, this is the particle, okay, then the ions very rigidly, because this particle we are thinking that this particle is having some kind of charge, okay, and this layer exactly adjacent to the particle, which is nothing but the counter ions, which are rigidly associated with the particle surface, is known as Stern layer, and basically these ions, if this particle moves, these ions actually also moves with the particle. Okay. Now there is this slipping plane over here. Okay. So this is the slipping plane over here. This plane is basically the plane of hydrodynamic shear, where where basically the particles do not move with the the ions doesn't move with the particle at all, and basically you can calculate or you can measure the potential at this slipping point, which is basically known as zeta potential. Okay, so this is the zeta potential, or plane of hydrodynamic shear. And the next one is basically your diffuse layer, where the counter ions and co-ions coexist, and the concentration of counter ions basically decreases where the co-ions increases, and obviously we have talked about this in the previous section. Okay, or this is basically known as the electrical double layer, where the ionic concentrations not the same as the bulk solution. There is a gradient in the concentration of ions outward from the particle until it matches to the bulk, and this is the bulk solution. So this is the whole dynamics of the particle, if you can think of. So basically if you just look at it, আমি এটাকে একটুখানি বড় করবার চেষ্টা করছি, আমি জানি না দেখতে পাচ্ছ কিনা তোমরা. So this is basically, this surface particle is having a negative surface charge. Then the positive counter ions comes very close to each other, and there basically you find the Stern layer, and then there is a shear plane where the slipping of the particle is happening.
ম্যাম আপনার অ্যারোটা দেখা যাচ্ছে না, অ্যারো গুলো।
Oh, so this is the shear plane where the particle basically or the slipping plane, where you can measure the zeta potential value, and this is the basically the bulk of the solution. So basically after this you have the bulk of, so this is the diffuse layer. Okay, so if you just look at this over here, so this is basically the Stern layer. This is basically the Stern layer. This is the shear plane where you can measure the shear zeta potential. This is the diffuse layer, and this is the bulk solution. Okay, and the total potential that you can measure over here, so at the surface is basically the surface potential, and at the shear plane the potential you will measure is known as the zeta potential. এই পরের এটাতে একটু বেটার বোঝা যাবে হয়. So zeta potential is nothing but the electrokinetic phenomena, which is the result from the differential movement of the two phases, where the interface is an electrical double layer, and the region containing the double layer is sheared at some distance from the solid surface, which is basically known as the shear plane. and the electrical potential at the shear plane is basically known as zeta potential. Okay, now we can measure the zeta potential by using the zeta sizer instrument, but before going to that, we can write the xi, that is the potential, will be equals to xi st into exponential minus kx minus st, because for us previously we have written this xi equals to xi naught into exponential minus k into x minus into x, right? কিন্তু এখানে দেখো আমরা জাইটাকে জাই এসটি দিয়ে রিপ্লেস করছি, just because it is impossible to measure the surface potential. Rather, what we will put or what we will measure is nothing but the start potential or the zeta potential. Okay, mostly we term it as zeta potential, and start potential is a bit আরেকটুখানি কনডেন্স স্ট্রাকচারের মতো, মানে যেখানে আয়ন্স গুলো কাউন্টার আয়ন্স গুলো একদম তোমার, তুমি যদি একটা ধরো চার্জ পার্টিকেল রয়েছে, একটা ডিসপারশন রয়েছে, ইলেকট্রোলাইটটাকে তুমি যদি জিটা সাইজারের মধ্যে দাও, যেখানে তুমি একটা ভোল্টেজ ইউ আর using or you are actually introducing a voltage difference, then you will see that there will be a mobility of these charged particles. Okay, and that mobility can be measured, and that can be, from that you can measure the zeta potential value. And in order to find how the potential of the surface potential will actually decay with the from the surface, you can use the zeta potential value or the stand potential value by using this equation over here. So আমি আর এগুলো বলছি না, কারণ এটা same thing has been what I have explained is written over here for your better understanding, যাতে তোমরা এতে পড়ে বুঝতে পারো. And this is another important point which is known as isoelectric point basically. So what happens is, when you are having zeta potential is highly dependent on pH. Okay, ionic strength as well as pH. Now at low pH, when you don't have enough OH or hydroxyl ion, so there will be an excess of positive charge, and you will find that the zeta potential value is something like this. When you have enough hydroxyl and hydronium ion, then you will see that your zeta potential is falling at 0 at the shear plane, and that is basically is known as isoelectric point. I will come to that. And when you have the high pH, when not enough H plus, so there is an excess of negative charges on the surface, and you find at the shear plane, and you find this kind of distribution of zeta. And if you put it together in one graph, how zeta is changing with pH, then you will find this kind of graph, and the point of 0 zeta potential is known as isoelectric point. Okay, so with increase
isoelectric point
so at the isoelectric point, what happens is you have enough coions and counterions present in the electrolyte, so the surface charge gets nullified. Fine.
Yes ma'am.
So that's where the zeta potential becomes 0, কারণ আমি তো surface potential মাপতে পারছি না, আমি zeta potential মাপছি. So at that position, surface potential becomes 0, and that is basically isoelectric point. Okay.
Please continue.
Okay, now with increase in ion concentration, you will see that there will be a decrease in zeta potential, and the values actually changes like this. Okay, but isoelectric point is directly related to pH, so that's why you might see that there will be a constant isoelectric point, although you are increasing the ion concentration, electrolyte concentration. Okay. Now, this is important, how we calculate the zeta potential value by using the microelectrophoresis. What happens is basically we do have, আমি এখানে দেখাতে পারছি না, আমার কাছে ওই পিকচার্স গুলো এই মুহূর্তে নেই, সো ল্যাবে আমরা দেখাই. So basically you do have a zeta sizer instrument which can actually use the electrophoretic mobility of the ions in a under a electric field, and that actually measured how much distance is covered within a certain period of time. From there, they calculate the electric potential or or the zeta potential by using either the Smolensky equation or the Haskell equation. Okay. Now, the UELF, that is nothing but the electrophoretic mobility, can be given by the electric drift velocity divided by the electric field strength, and this electric drift velocity can be given as dx/dt, where x is nothing but the distance covered at a certain time t, and ex can be given in terms of u by l, that is the electric field strength. Okay, that is volt per centimeter in that format. Now, once you know this UELF, then that is the electrophoretic mobility, you can put that into these equations. Zeta will be given in terms of UELF eta divided by epsilon r. Epsilon eta is the refractive index of the medium, as well as refractive index of the medium, and epsilon r is the you can put it in terms of epsilon relative permittivity, and you can for big particle thin double layer you can use Smolensky equation, and for small particle with very thick double layer you can use Haskell equation, where zeta can be given in terms of 3/2 UELF eta divided by epsilon r. Okay, now I had planned couple of problems for you, but I'm not sure how many I can do. But this I'm not going to solve because this is a direct one, which you have to, if you just look at it, I don't know whether you can see it properly. It's a bit small. আমি একটু বড় করবার চেষ্টা করছি. Okay, so basically it is for you have to consider two ions, Cl minus, N plus, and also the distance r. What is the inter-ion potential energy for both the distance, and calculate the potential energies as a fraction of. এটা তোমরা পারবে, এটা আমি করে দিচ্ছি না, ঠিক আছে? করে দিচ্ছি না মানে আমি এটাকে হয়তো মানে এমনি যখন নোটস পাঠাবো তখন করে দেবো, কিন্তু এই মুহূর্তে ক্লাসে করছি না। ক্লাসে আমি একটাই প্রবলেম আজকে করব, এই প্রবলেমটাও আমি করে দেব। যে প্রবলেমগুলো লিখে রেখেছি সবকিছুই, এই প্রবলেমগুলো ইজ ডাইরেক্ট অ্যাপ্লিকেশন অফ হ্যামাকা কনস্ট্যান্ট ইকুয়েশনস দ্যাট উই হ্যাভ ইউজড। আচ্ছা, আমি লাস্ট ক্লাসে না যখন নোটসটা দিয়েছি একটা জিনিস আমি একটুখানি বলে দিচ্ছি। হ্যামাকা কনস্ট্যান্টস এর আমি একটা জাস্ট চোখে ভুল দেখতে পেলাম যখন এই প্রবলেমটা, দেখো A11 অ্যান্ড আমি ব্র্যাকেটটা দিতে ভুলে গেছি। তোমরা সিম্পলিফাই করলে তোমরা ওটা নিজেরাই করে নিতে পারবে, কোনো অসুবিধা নেই, কিন্তু ফাইনাল নোটসেও ওই ব্র্যাকেটটা নেই, যার জন্য ওটার মিনিংটা আলাদা হয়ে যাচ্ছে। এক মিনিট দাঁড়াও, আমি ওটাকে বার করছি। আমি তাহলে ওই 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 লেকচারটা ওখান থেকে ইয়ে করে নিয়ে আর একবার ওটাকে প্রেস করে দিয়ে দেবো, হ্যাঁ? আদারওয়াইজ ওই ইকুয়েশনটা যেহেতু আমরা অনেকটা ইউজ করব, প্রবলেম হবে তোমাদের।
ঠিক আছে,
দাঁড়াও একটুখানি নোট করে নাও, প্লাস আমি যদি বাই চান্স না দিয়ে থাকি তাহলে যেন একবার নিজেরা ওটাকে করে নেবে। আমি করে দেব, কিন্তু জাস্ট বললাম। কারণ আমারও দেখতে কি কিরকম মনে হচ্ছিল। হ্যাঁ, এই ইকুয়েশনটা দেখো, আমি না এইখানের এই ব্র্যাকেটটা, একটা ব্র্যাকেট থাকবে, হ্যাঁ, আদারওয়াইজ এটার মিনিংটা একদম আলাদা হয়ে যাচ্ছে। ওকে,
এইখানে একটা জিনিস জিজ্ঞেস করা,
এটা ক্লাসে মনে বলেছিলেন।
হ্যাঁ, মানে এইগুলোকে যদি তুমি সিম্পলিফাই করো নিজে তাহলে ইউ উইল অবটেইন দিস। মানে আমি সেটা জাস্ট বলে দিলাম কারণ আমার চোখে পড়লো সেই জন্য।
ওকে
ম্যাম, এখানে একটা জিনিস জিজ্ঞেস করার ছিল, যদি A33 টা A11 আর A22 এর মধ্যে লাই করে তাহলে ম্যাম ওটা কি অ্যাট্রাক্ট করবে?
A33 টা
A11 আর A22 এর মধ্যে যদি লাই করে,
A33 টা যদি A11 আর A22 এর মধ্যে লাই করে,
হ্যাঁ
আহ, A33 A11 A22 এর মধ্যে লাই করছে, তাহলে এটা নেগেটিভ হয়ে যাবে।
A132 টা নেগেটিভ আসবে।
হ্যাঁ, তাহলে এটা আমি উল্টো লিখেছি, লেখাটা উল্টো হয়েছে, তার মানে এটা তো হ্যাঁ নেগেটিভ হবে,
Attract করে।
তাহলে ওরা অ্যাট্রাকশন হবে, ঠিক আছে?
হ্যাঁ ম্যাম, তো এইখানে দেখুন আপনি লিখেছিলেন রিপেল ইচ আদার।
হ্যাঁ হ্যাঁ হ্যাঁ, ওখানটা দাঁড়াও 1 মিনিট, সরি, আমি এখন দেখছি যে ওটা হ্যাঁ দেখো এখানেও তাই লিখেছিলাম, এখানে ভুল করে ওটা লিখেছিলাম, এটা একদম ঠিক নয়, এটাও আমি একটুখানি করে নিবে, এটা হচ্ছে তোমার অ্যাট্রাকশন হবে, রিপালশন।
ইয়েস ম্যাম।
যখনই টোটাল এনার্জিটা বা টোটাল হ্যামারকা কনস্ট্যান্ট নেগেটিভ, তখন ওটা সবসময় হচ্ছে তোমার অ্যাট্রাকশন। আর না না, 1 মিনিট দাঁড়াও, না, A33 টা যদি নেগেটিভ, মানে এইটা যদি A132 যদি নেগেটিভ হয়, টোটাল এনার্জিটা কিন্তু পজিটিভ হয়ে যাবে, তখন কিন্তু রিপালশনই হবে। বুঝেছো? ইজ ইট ক্লিয়ার? না
ইয়েস
মানে this becomes negative, right? Now you are putting negative value of Hamarka constant into this equation. Already একটা নেগেটিভ সাইন রয়েছে, সরি এখানে রয়েছে, অলরেডি একটা নেগেটিভ সাইন রয়েছে, তাহলে এটা পজিটিভ হয়ে যাবে, রাইট? So you will get the force as positive which will repel each other, ঠিক আছে?
ওকে ম্যাম, ইয়েস।
That is fine, it's only that thing. Okay. আমি একটা খালি প্রবলেম করব, আমি অনেকগুলো প্রবলেম লিখে রেখেছি, আমি প্রবলেমগুলো ডিটেলসে করে নিজে করে দিয়ে দেবো তোমাদেরকে, হ্যাঁ? খালি যদি তোমরা বুঝতে না পারো, তখন আমরা একটা দুটো প্রবলেম করে নেব, আমি বুঝিয়ে দেবো, ঠিক আছে? কারণ এখন এতটা সময় হবে না। আমি কোন প্রবলেমটা করবো ভাবছিলাম, এই যে জিটা পটেনশিয়ালের এই প্রবলেমটা আমি করে দেবো, ঠিক আছে? আর অন্য প্রবলেমস গুলো আমি সলভ করে আজকে রাত্রির মধ্যে তোমাদেরকে দিয়ে দেব, তারপর তোমরা যেটা করবে মানে তোমরা একটুখানি দেখে নিও, যদি তোমাদের মনে হয় যে একটুখানি সলভ করতে হবে তাহলে করবো। এই প্রবলেমটা আমি পুরো হয়তো সলভ করবো না, আমি মানে জাস্ট ইনিশিয়ালি কিভাবে সলভ করতে হবে সেটা বলে দেবো, ঠিক আছে?
ওকে ম্যাম।
Okay, so basically the following data are available from a measurement of zeta potential in an aqueous suspension of kaolin particles at 25 degrees Celsius. Diameter of the spherical particle is given, concentration of NaCl in water is given, movement of the particle is 360 micrometer, time for the movement of the particle is 4.6 seconds, potential of the field is 10 centimeter cell is 200 volts. Moreover, the following values are available for if correction parameters of the Henry's equation. আমি যদিও Henry's equation পড়াইনি, বাট আমি এখানে একটুখানি বলে দেবো, বলে দিয়ে আমি পুরো প্রবলেমটা সলভ করবো, কারণ আমি দুটো ইকুয়েশন বলেছি, একটা হচ্ছে either স্মোলস্কি অর হাকেল। যদি Henry's equation বলে না দেওয়া থাকে, ইউ ক্যান ইউজ মানে কেন আমি স্মোলস্কি অথবা হাকেল ইউজ করছি না সেটাও এখানে বলবো, আর Henry's equationটা এখানে বলে দেবো, সেই জন্য এই প্রবলেমটা বেসিক্যালি দিয়েছি। So you have to calculate the electrophoretic mobility of the colloid particles, provide an estimation for zeta potential of the particles, and mention the example of how zeta potential can be changed, and there are whole sort of things. But let us go ahead with the problem. Okay, so first we will start writing about the force. So basically nothing but force we can write minus d va or d whatever term you are using in if h is the distance, so we can put it minus 6, sorry, minus r into a divided by 6 h square. We have already basically written all these equations, so basically we can put it in terms of r 1 2 3 because there are, you know, this is basically a particle moving in NaCl water. All these things are there, so we have to go for that. No, because they have said এটা ঠিকঠাক বললেন। আচ্ছা, এই প্রবলেমটা করালে এই প্রবলেমটা একটু বেশি সহজ। আর একটা প্রবলেম ছিল, ওই প্রবলেমটা থাকলে ভালো হতো। তারও 1 মিনিট দেখছি আমি ওই প্রবলেমটা নিয়েছি কি নিইনি। এটা তো কাউলিনের প্রবলেমটা। তারও 1 মিনিট, এই প্রবলেমটাও করিয়ে দিতে পারি। আর একটু দেখে নি ওই প্রবলেমটা আছে কিনা, ওই প্রবলেমটা বেটার প্রবলেম আছে। নয়তো এই প্রবলেমটাই করিয়ে দিচ্ছি। ঠিক আছে, এই প্রবলেমটাই করিয়ে দিচ্ছি। এই প্রবলেমটা সহজ কম্পারেটিভলি একটুখানি। ঠিক আছে, এটা হচ্ছে ইলেকট্রোফোরেটিক মোবিলিটিটা জানতে চেয়েছে, সো আমি ডাইরেক্টলি ওখানেই চলে যাব। আচ্ছা, এখানে তাহলে ভ্যান্ডার ওয়ালস ফোর্সেসের দরকার নেই এই মুহূর্তে। ওখানে হচ্ছে তোমার ইলেকট্রোফোরেটিক মোবিলিটিটা জানতে চেয়েছে, দ্যাট মিনস যেটা পোটেনশিয়ালের ক্যালকুলেশনস গুলো লাগবে আমাদের। সো বেসিক্যালি ক্যালকুলেট দ্য ইলেকট্রোফোরেটিক মোবিলিটি। সো উই ফার্স্ট রাইট দ্যাট, মানে এখানে অলরেডি উই হ্যাভ রিটেন দ্য ইকুয়েশনস for zeta potential. So UELF equals to VELF by EX, সেইটা, and EX values are given. Then VLF equals to dx dt জায়গায় আমরা x by t ফর্মে লিখতে পারি, তাহলে আমাদের পুরো ইকুয়েশনটা will come up to UELF will be equals to x by te, okay, in that format. So we can write u equals to the, এই প্রবলেমটা অনেক সহজ প্রবলেম, আমি অ্যাকচুয়ালি একটা অন্য প্রবলেম করাবো ভাবছিলাম। d ডিভাইডেড বাই, আচ্ছা ভিটাকে যদি আমি লিখিও আমার অসুবিধা নেই লিখতে। সো v by ex, vটাকে we can write it in terms of d by t into e in that format, or x by t into e, whatever you want to write, and that basically gives us the value of, already this value is the movement of the particle, the distance is given 360 micrometer, time is given as 4.6 seconds, whereas the potential of the field is given as 200 volts, and so we can put all these values over here in order to obtain the u value, which will come around. So we can put 360 into 10 to the power minus 6 divided by 4.6 seconds into 200 volt for 1 meter, sorry, 0.1 meter 0.1 meter cell. So we have put it like that way, and this will give us a value of 3 point whatever 913. You can do the calculations. I'm just putting the final value over here, minus 8 meter square per second per volt. Sorry. Okay, and then they have asked for, so this is the electrophoretic mobility of the colloidal particles. You have to provide an estimation of the zeta potential of the particles. Mention one example how the zeta potential can change. Now I haven't mentioned this, but usually in this, if I provide this kind of problem, then obviously your data will be provided. So in one of the table, we found that for 1:1, this is part 1, this is part 2, for 1:1 electrolyte, A inverse is given as 0.8 equation তোমাদের দিয়ে দেওয়া থাকবে 0.304 divided by the concentration. Okay, now here the concentration is concentration of NaCl is 0.003 meter. So we can put that value over here in order to obtain what will be the K inverse value, and from there we can calculate what will be the value of A. K inverse is coming around 5.55 nanometer, and K will be inverse of that. So this will be around 1.8 into 10 to the power 8 meter inverse. Now KR, কেন আমি KR ভ্যালু করছি তাহলে আমি বলবো সেটা পরে, 45.05 around this. Okay, now over here if you look at it, KR is not less than 0.1 or greater than 100. Okay, if it is greater than 100, sorry, it is greater than 100, not greater than 100, not less than equals to 0.1. Now if it is KR is basically greater than 100, then we can go for the Smolowski equation. No, sorry, Huckel equation, where we have said that D by length বেশি. So this is Huckel equation, sorry, this is Huckel equation, and this one will be your Debye equation. So এইটার দুটোর মধ্যে কোনোটাই হচ্ছে না বলে we have to go for Henry's equation, where Henry's equation actually gives us the value of like psi naught equals to 1.5. Mu is the electrophoretic mobility over here, N is the refractive index divided by epsilon into epsilon naught F AR. Event. Okay, so from this we know all these values, so we can find out what will be the value of psi naught. Okay, and that is basically we can put it in the form of the zeta potential, because we cannot directly use the Debye equation or the Huckel equation. So this is, so the value comes around, আমি লিখে দিচ্ছি ফাইনাল ভ্যালুটা, তোমরা নিজেরা করে দেখে নিতে পারো। আমি যখন লিখবো, মানে আমি যখন প্রবলেমটা পুরোটা করে দেবো, তখন আমি উইথ এক্সপ্লেনেশন সবকিছু লিখে দেবো, তাহলে তোমাদের সুবিধা হবে। আমি ওই ইকুয়েশন ওই প্রবলেমটা নিলামই না। ঠিক আছে, আমি আরো একটা প্রবলেম এখানে ইনকর্পোরেট করে লিখে দেব, ইনকর্পোরেট করে দেবো, সেইটা আর কি করে দেবো। তাহলে এখানে একটা অন্য একটা প্রবলেম করে নিই, কারণ এখানে বাকি যেগুলো আছে সেগুলো হচ্ছে তোমার এমনি zeta potential is often less important system or organic solvents. Explain briefly why. How can kaolin suspension be stabilized in a solution with an organic solvent? এটা বেসিক্যালি with steric stability. ওকে, সো এই লাস্টে 2, 3 আর 4টা তোমাদের দরকার নেই, আমি এটা কেটেই দিচ্ছি। এই জায়গাটা কেমিক্যালের লোকজন ছাড়া একটুখানি অসুবিধাই হবে। ওকে, সো আর একটা দেখছি, এইটা সেম হয়ে গেছে না, সেই জন্য প্রবলেম হয়ে গেছে। এনিওয়ে, আরেকটা প্রবলেম করিয়ে দিই, দেখা যাক। আচ্ছা, না তো আমি আজকে ছেড়ে দিচ্ছি, ঠিক আছে, 6টা বাজছে, আই হ্যাভ টু গো ব্যাক ফ্রম ইউনিভার্সিটি। তো আমি আজকে এখানে ছেড়ে দিচ্ছি, আমি এই প্রবলেমগুলো সবকটাই করে দেব কিন্তু, ঠিক আছে, উইথ 1 or 2 মোর অ্যালং উইথ ইট।
ওকে ম্যাম, ওকে ম্যাম, থ্যাংক ইউ।
বলছিলাম একটু এক্সপ্লেনেশনের সাথে একটু করে দিলে
হ্যাঁ, এক্সপ্লেনেশনস গুলো আমি দিয়ে দেবো, যদি তোমাদের বুঝতে অসুবিধা হয় তাহলে নেক্সট ক্লাসে আমাকে জিজ্ঞাসা করে নেবে। হ্যাঁ,
ওকে ম্যাম, ওকে।
ওকে ম্যাম। আর বলছিলাম নেক্সট ক্লাস তো কালকে হবে না?
হ্যাঁ বলো।
বলছিলাম নেক্সট ক্লাস তো কালকে হবে না?
নেক্সট ক্লাস কালকে?
তাই তো ঠিক হয়েছিল একটা ওরকম।
কখন?
আরে আমাদের ম্যাম বলেছিল না একটা এক্সট্রা ক্লাসের দরকার আছে, তো তো এই ক্লাসটা একটু এক্সটেন্ড করে দেওয়া হবে নাকি অন্য দিন একটা ক্লাস নেওয়া হবে, একটা এরকম ডিসকাশন হয়েছিল না?
হ্যাঁ, আমি বলেছিলাম বটে, কিন্তু কালকে আমার একটা ভাইভা আছে। তোমরা কটা থেকে ক্লাস করতে চাও বলো তো কালকে? একটু আমাকে বলবে। আমার হঠাৎ করে মানে ওই ভাইভাটা আর কি, মানে আউট অফ, মানে ওটা প্ল্যান্ড ছিল না, হঠাৎ করে ওই ভাইভাটাকে এগিয়ে আনতে হয়েছে, কারণ যেহেতু ওটা এতে রয়েছে। সো তোমরা কালকের ক্লাসটা আমি হয়তো নিতে নাও পারতে পারি, মানে ভাইভা কটা শেষ হবে আমি এক্স্যাক্টলি
এই পোর্শনটা তো ম্যাম আমাদের মানে ক্লাস টেস্টে তো নেই।
না, এই পোর্শনটা ক্লাস টেস্টে নেই।
তাহলে কি নেক্সট ক্লাসটা ক্লাস টেস্টের পর করালে হবে?
ক্লাস টেস্টের পর কিন্তু ওই উইকটাতেই লাস্ট ক্লাস হবে, কিন্তু তারপর কিন্তু ক্লাস ডিসলভ হয়ে যাবে, তাই না? আর 25 তারিখটা লাস্ট ক্লাস হবে, ঠিক আছে? তাহলে ওই উইকটায় আমাকে 1-2 ক্লাস এক্সট্রা কিন্তু দিতে হবে, একটুখানি খেয়াল রেখো।
আচ্ছা,
একটু প্রবলেম হয়। নেক্সট উইকে আমাদের তো ক্লাস টেস্ট আরো আছে।
তোমাদের এখনো ক্লাস টেস্ট সব শেষ হয়নি?
না ম্যাম,
পর আছে,
4টে ক্লাস টেস্ট বাকি আছে ম্যাম।
4টে ক্লাস টেস্ট বাকি? কি গো,
ক্লাস দুটো পাইবা
ম্যাম? অ্যাকচুয়ালি আমাদের 6টা সাবজেক্ট ফাইনাল সেমিস্টার।
সেটা আমি জানি, কিন্তু মানে আমাদের ক্লাস টেস্ট গুলো অনেক, খালি আমাদের 8 সাবজেক্টেরই ক্লাস টেস্ট এত দেরিতে নেওয়া হচ্ছে। আমাদের ক্লাস টেস্ট অনেক দিন আগে হয়ে গেছে, তাই সেই জন্য বলছি।
আমার সব বাকি, আপনার পরের দিন আরেকটা আছে, তারপর নেক্সট উইকে পরপর দুটো আছে, তারপর ভাইভাও আছে।
কারণ শনিবার দিনটা আমি হয়তো পারবো না, মানে শনিবার দিনটা আমি ভাবছিলাম ক্লাসটা নিয়ে নেব, কিন্তু ক্লাসটা বোধহয় নিতে পারবো না, আমি একটু বাইরে যাচ্ছি সেই জন্য। আচ্ছা, কালকে কটা থেকে ক্লাস করবে আমাকে বলে রাখো একটুখানি, বাই চান্স যদি ভাইবা শেষ হয়ে যায় আমি ইনফর্ম করে দেবো।
ম্যাম তাহলে একবার একটুখানি মানে সন্ধ্যার দিকে আপনাকে জানিয়ে দেবো, মানে কোন সময়টা আমাদের কালকে বা পরশু যদি থাকে, তাহলে কোন সময়টা কি?
পরশু হবে না, পরশু আমার হবে না।
আর ম্যাম বলছিলাম মানে কি মানে পুরো সিলেবাসটাই রাখতে হবে সেমিস্টারে, একটু শর্টেন করে রাখলে হয় না?
হ্যাঁ ম্যাম, একটু যদি কমানো যায়।
একটু কমানো কি, পড়িয়েছি তো এতটুকু, আমি তো মানে বুঝতেই পারছি না যে কোয়েশ্চেন কোথা থেকে করব।
এটাও তো অনেকটা মনে হচ্ছে।
পুরো সিলেবাসটা তো পড়ানোই হয়নি এখনো। আর কন্ট্যাক্ট অ্যাঙ্গেলটা আমি খুব শর্টে পড়াবো, এটা আমি তোমাদেরকে বলেই দিচ্ছি। কারণ হচ্ছে যে ওখানে আমি জাস্ট কিছু ইকুয়েশনস দেখিয়ে দেখিয়ে বেরিয়ে যাবো, আর ছোট ছোট প্রবলেম করে করে যে চলে যাবো ওখানে।
আচ্ছা ম্যাম, কালকে ম্যাম সেকেন্ড হাফে হবে ম্যাম কোনো সময়, মানে
সেকেন্ড হাফে
আড়াইটায়?
অ্যাকচুয়ালি কালকে আমার 11টা থেকে 1টা অবধি ক্লাস আছে, তারপর 2টো থেকে আমার ভাইভা আছে।
ভাইবার পরে তাহলে ম্যাম সেকেন্ড হাফে আপনি যখন বলবেন আর কি।
আচ্ছা ঠিক আছে, আমি ইনফর্ম করে দিচ্ছি। ঠিক আছে, তোমরা মোটামুটি 4:30, 4টে 4:30 এরকম ধরে রাখো। ঠিক আছে,
ওকে
হোপফুলি
ওকে
4টে 4:30-র মধ্যে ভাইভা ওভার হয়ে যাওয়ার কথা। ঠিক আছে
আচ্ছা 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 ঠিক আছে।
ঠিক আছে, বাই চান্স কিছু প্রবলেম হলে আমি ইনফর্ম করবো, আদারওয়াইজ ওই পরের মঙ্গলবারটা একটু এক্সটেন্ড করবো। আমি সেদিনকে বাড়িতে থাকবো, আজকে অ্যাকচুয়ালি ইউনিভার্সিটি আসতে হলো, যার জন্য ইউনিভার্সিটিতে তার একটু বেশিক্ষণ এক্সটেন্ড করতে পারছি না। কালকে সেদিনকে বাড়িতে থাকলে একটু বেশিক্ষণ পড়িয়ে দেবো। হ্যাঁ
ওকে ম্যাম ওকে।
শিওর ম্যাম।
ঠিক আছে ম্যাম।
ওকে, থ্যাংক ইউ।
থ্যাংক ইউ ম্যাম, থ্যাংক ইউ।